in this section, we'll discuss energy considerations for one-dimensional systems. This section discusses relationships having to do with the energy in simple one-dimensional systems. And now it's important to note here, when we say one-dimensional systems, we don't necessarily mean that the physical position of our object of interest is only given by one positional coordinate. What we mean here is that the system has a single degree of freedom so that its motion and mechanical energy can be captured by just thinking about a single physical coordinate. So for example, if we imagine we had a roller coaster car sitting on a roller coaster, the position of that roller coaster car depends on x and y and also z, but because the roller coaster car is constrained to lie on the track somewhere, in reality we can describe its position by just giving one coordinate. So in this case we could just give the x coordinate, and by specifying x and a relationship between y and x which describes the shape of the roller coaster track, we can describe the motion of this roller coaster car just using x. So this would be an example of a one-dimensional system where in fact the motion takes place in two dimensions. Okay, so what's important here is that there's one degree of freedom, not necessarily that the system is constrained to move along one coordinate. And so the book discusses these kinds of systems. They're particularly simple. There's lots of useful relationships you can work out by just thinking about the energy of the system. And so to illustrate that, I'm going to work problem 4.28 from the back of this chapter to show how we can use energy considerations to actually work out the dynamics of a one-dimensional system. So here's a basic physical setup for the system described in problem 4.28. We've got a mass, m, at the end of a spring with a spring constant k. This mass can only move back and forth along the x direction, and so we're going to measure the displacement of this mass from equilibrium, that is, from the point at which the spring is no longer pushing or pulling on the mass. We're going to measure that displacement from equilibrium using the coordinate x. And the problem specifies that we imagine the system starts out at equilibrium, so the mass is at x equals 0, and we give it an initial kick, just hit it real hard and send it flying off in one direction, so that it actually moves out to x equal a, so the maximum value for x, in other words the amplitude for the oscillation. And we're asked to work out several different aspects of the system using just energy conservation. So remember that the total mechanical energy of the system is going to be the kinetic energy of motion plus the potential energy having to do with the spring. So let's look at that. The first part of the problem asks us to work out what the energy is and then use the energy to solve for the velocity x dot. So part A, we're asked to use the energy conservation to work out the relationship between the velocity of the mass x dot and its position, and then the energy, of course. So here's our total energy again, kinetic plus potential. The kinetic energy is going to be 1/2 mass of the oscillating object times the velocity squared, and then the potential energy is going to be the potential energy associated with the spring, so that's going to be 1/2 spring constant k times the displacement from equilibrium squared. And this all has to be equal to the total energy in the system, whatever that is, whatever it starts out as. So we can rewrite all this equation and solve for x dot, and just sort of skipping to the solution, you get a solution that looks like this. X dot is going to be equal to the square root of 2e over m minus k over m x squared. And so the basic idea is we start out the system with some initial energy. In the case of this problem, we are kicking the mass in a certain direction, so we're giving it an initial kinetic energy. And this relationship tells us that the velocity of oscillation will drop as x increases, so as the mass moves away from equilibrium, as x increases in either direction, in fact, until this term here is exactly equal to this term here. At that instant, x dot is going to be 0. In other words, the mass is going to stop moving. Let's look at part B. Part B asks us to show that the total initial energy of the system, E, is given by 1/2 k a squared, so that maximum amplitude. So remember, we're imagining that we give the mass a kick and it heads off in a certain direction with an initial velocity till it stretches out to a maximum distance a. So that's the amplitude of oscillation. So if that's the maximum distance from the equilibrium position, x equals 0, at that point the velocity has to be 0. In other words, the mass is going to move out with a non-zero velocity until it reaches the maximum amplitude, and then it's going to stop. And so when x is equal to the maximum amplitude, the velocity is 0. And so as you just discussed, in order for x dot to be 0, all of this under the radical has to be 0. So therefore we require that 2e over m minus k over m a squared is equal to 0. And you can see if you solve for e in this equation that you'll get that e is equal to 1/2 k a squared. Okay, so that's the total energy of the system. That's the initial energy we're given. Since energy is conserved, that's the energy throughout the entire problem. So let's incorporate this back into this equation and rewrite the velocity using that. Okay, so here we go. Remember, our total energy for the system is 1/2 k a squared. We've already solved for x dot in terms of those things, so let's plug in this expression here in here and solve for x dot. We do that, and we find that x dot is equal to this. So it's going to be square root of k over m times the square root of a squared minus x squared. Now remember that x, the maximum, the displacement from equilibrium, is never bigger than a. And so x squared is always going to be equal to or smaller than a squared. And so this term under here in the radical is always going to be a positive number or 0. And so we're never going to get any imaginary numbers here. We're never going to take the square root of any negative numbers. Okay, so for the next part of part B in this problem, we're asked to use a relationship 4.58 from earlier in the chapter to work out what t is as a function of this integral. So we've got t is equal to the integral of dx prime over x dot, which is itself a function of the integration variable x prime. I want to integrate this from x prime equal to 0 up to whatever the maximum amplitude is. And when we do that, that'll give us, that'll tell us the amount of time it takes for the oscillator to go from equilibrium all the way out to the maximum amplitude. In other words, that'll be related to the period of oscillation. Okay, so now we're going to plug in this equation here into this and then do an integral. We'll see how that looks. Okay, so again, x dot is given by this. We'll plug in that x dot into this equation, and here now we're going to integrate not up to a, but we'll integrate up to some x, which will turn out to be a function of time. So what we're going to do is end up inverting this whole relationship to get x as a function of t. Okay, and so now we've got to do this integral. This is the tricky part here. Now you may recall in class that I told you when you had an integral that looked something like this, when you had 1 over the square root of some stuff squared, or the square root of 1 plus some stuff squared, or anything like that, often it pays to consider some kind of a trig substitution, where we're going to define a new variable for x prime here. Excuse me, this should be x prime. And so let's try a trig substitution like this. X prime, excuse me, let's call x prime a times the sine of a new integration variable theta. Okay. Now it's important that we put an a up front here times the sine. We couldn't just say x prime is equal to sine theta because sine theta goes from 0 to 1, or say -1 up to 1. But x prime, the integration variable here, we know that that can go all the way up to a. Okay, so we have to append an a at the front here in order to make, in order to allow our x prime variable to take on the full range of values it's allowed. Okay, so if x prime is a sine theta, then we can see that dx prime is going to be a cos theta d theta. Okay, and then we need to look at our limits for our integration. We're going to integrate, remember, from x prime equals 0. Okay, and so when x prime is equal to 0, theta is equal to 0. And when x prime is equal to x, why then theta is going to be the inverse sine of x over a. Okay, and so we're going to plug these relationships in to our integral here and work out t. Let's see what we get. Okay, so plugging in, we get this relationship between t. Here's our integral over here. Here's our dx prime, and then here's x prime down here. We can see that we can pull out an a squared from each of these terms. A squared, take it to the square root. It's just going to give us a. We're going to a up here, so the a's are actually going to cancel out. So let's do that, and we get the following. Okay, so having pulled the a out, here we go. We've got cosine theta d theta, and then square root of 1 minus sine squared theta. Hopefully this looks familiar. 1 minus sine squared theta, that's going to be cosine squared theta. Cosine squared theta, take a square root, that's going to give us cosine. So we've got a cosine on top, we'll have a cosine on bottom. And so then we can see that the cosine is going to cancel, and then this integral is just going to become, the whole expression is just going to become this, square root m over k, integral from 0 to inverse sine theta of, remember, x over a, integral d theta. Well, that one's pretty easy to do. We find that this integral is just going to become square root m over k times the sine, inverse sine of x over a. And that's all equal to t. And so given some distance, x, we can figure out how long it takes the oscillating mass to move out to that position. And for part C, we're asked to show that the motion described by this equation is in fact simple harmonic motion. Part C, we're asked to show that motion of the system is simple harmonic motion with a period equal to 2 pi square root m over k. And hopefully you can see that if you solve this equation here for x as a function of t, you get something that looks just like that. So let's see what that looks like. Here's the solution, x of t. And hopefully this looks familiar. We've got a, our amplitude, times the sine of something times t. You can see that when t is equal to 1 over, when t is equal to 2 pi times square root of m over k, that corresponds to 1 full oscillation for this guy here. In other words, the period is equal to that. So we've got simple harmonic motion with a period given by this. That's the solution to problem 4.28.